Hello everyone, welcome back to our course Network Theory and Transmission Lines, and today's discussion is about the resonance in RLC circuits. So at resonant frequency, what is the behavior of the resistance, inductance and the capacitance? Right? How these elements is going to get varied and how the response of this RLC circuit is going to be there at the resonant frequency. And what is the bandwidth value is going to be at resonant frequency. These are all we are going to discuss in today's lecture. And these are the outcomes of the presentation. So we are going to look into the RLC circuit at resonant. We are going to get the expression for the resonant frequency and quality factor and bandwidth. So what do you mean by resonance? Then very first, you might have heard this term in your physics. So resonance, when a material or any kind of object is moved with some applied or external force, it is going to oscillate or it is going to vibrate at some frequency, right? The frequency at which the object is going to have the maximum output or the maximum vibration is nothing but your resonant frequency. That's what we have done with respect to the simple pendulum experiment in your 8th standard or 9th standard. I couldn't remember exactly. Right? So here, coming to our electrical circuits, what do you mean by this electrical resonance? As stated here, the electrical resonance is going to occur in electrical circuits at a particular resonant frequency when the impedances or admittances of the circuit elements is going to get cancel each other. So that means at that point the resistance is going to be the minimum. At that particular resonant frequency, the resistance is going to be the minimum. Right? So another way, if you want to define or elaborate the resonance in electrical circuits, so here, coming to the electrical circuit, what is our electrical circuit here? Here, our electrical circuit is, so here in our electrical circuit is with respect to the RLC, right, which is a passive and active elements with respect to, if you want to speak, the particular state of a circuit, when the current or voltage in the circuit is maximum or minimum with respect to the magnitude of excitation. This is going to be applied or external source at a particular frequency. Right? At this frequency, the condition is the circuit impedance could be being either minimum or maximum at the power factor unity. Right? At the power factor unity, the circuit impedance could be minimum or maximum. So here there is a word that is the power factor unity. So when we can have this unity power factor. So in a circuit, right? In an electrical circuit, the power factor is going to be unity when the angle between, if you draw the, I think we might have know about the phasor diagrams, right? So if you go for the phasor diagram of an electrical circuit, so when the power factor is going to be unity means the angle between the voltage and the current is going to be equal to 0. So when it is going to be equal to 0, when the circuit impedances is going to be minimum at that point, that is going to have the power factor unity, right? So here, so let us consider a series resonant circuit for our understanding purpose. Let us consider a series resonant circuit where the resistance, capacitance, and the inductors are connected in a series. So we will come across this omega naught equal to 1 by root over LC, which is nothing but our resonant frequency value. We will come across this. So here AC source is applied and we are having I is equal to V by Z is nothing but your impedance. So till now, we have considered I is equal to V by R. So here, when we are considering the AC circuit with a combination of different elements like inductor and the capacitor, the impedance is going to come into the picture. So impedance is nothing but the resistance itself, but here with respect to the AC resistance. So AC resistance is also known as the impedance. So many people may have a confusion in this between the what is the difference between the impedance and the resistance. So if we speak with respect to the DC circuit, then we will call it as the opposition offered in the circuit is known as your resistance. So, but when we go for the analysis of the AC circuit, the opposition to the current offered in the circuit is nothing but your impedance. This impedance is nothing but is going to have a, so when we come across the AC component, so if we write the expression for the impedance, so Z is nothing but Z is equal to R, the resistance R with some phase, So it can be of theta. So here, why? Because here phase, we are speaking with respect to the phase in the sense. So this is nothing but due to the, here we are having a AC excitation, right? Here we are having a AC excitation. So here, I think the basic, if you want to derive the equivalent impedance of a simple RLC circuit, so R plus, so XC, the capacitance is going to offer some reactance. XC is nothing but your capacitive reactance, and XL is nothing but your inductive reactance. So this combination of this resistance R plus XL and XC is going to be your overall impedance of your RLC circuit. So let us go into the equation part of this impedance in the next slide. So what is this inductive reactance? XL. So XL is nothing but omega L, which is equal to 2 pi FL, which is equal to 2 pi FL. Omega is nothing but 2 pi F, right? So which is equal to 2 pi FL, and the capacitive reactance is nothing but XC, which is equal to 1 by 2 pi FC. 1 by 2 pi FC. So when we are writing the impedance equation, so let me give you a small explanation on this. So when we are writing the impedance of an RLC circuit, Z is equal to, we can write R plus J omega L plus 1 by J omega C. 1 by J omega C is your impedance expression. So here R is your resistance and this omega L is your inductive reactance, because here this inductance as capacitance is going to be our complex quantity over here, the inductive reactance and the capacitive reactance. So that is the reason why it is in terms of J complex, right, which is equal to, if you want to write the same expression in other form, R plus J omega L, I'm writing the same, R plus J omega L plus, so I am making this plus to minus. Why? Because I am multiplying with J in the numerator and the denominator. So minus, so J square is going to become minus 1. So minus J by omega C. J by omega C. So which is equal to, again I can write the same equation as R plus taking J as common, R plus J into omega L minus 1 by omega C. 1 by omega c. This is going to be our equation. So R plus J into omega L minus 1 by omega c. If you are having only a RL circuit, then the impedance is going to be equal to R plus J omega L. If it is a RC circuit, the equivalent impedance is going to be equal to R minus J omega C, J by omega C. If it is a RLC circuit, R plus J into omega L minus omega 1 by omega C. So what is this omega L? Omega L is nothing but the inductive reactance XL. What is this 1 by omega C? 1 by omega C is nothing but your capacitive reactance 1 by omega C. So in a circuit, in a RLC circuit, say for example, if this inductive reactance is getting dominated with respect to the XC, that means here XL is greater than XC. So obviously the circuit is going to be more inductive. So if we consider the other case, that is XC is greater than XL, that means here the inductive capacitance is going to get dominate. So here the circuit is going to be more capacitive in nature. If you want to write the expression for the total circuit reactance, the total circuit reactance is going to be equal to XT is equal to XL minus XC. Right? Why? Because so the reactance is nothing but the reactance of our RLC circuit is nothing but it is nothing but the resistance offered by our inductance and the capacitance. So what is that reactance offered by the inductance? It is nothing but J omega L, and it is other one is nothing but J by omega C. So if we consider only the magnitude, then we can have omega L minus 1 by omega C is going to be our reactance, total circuit reactance. So resistance plus reactance is nothing but your impedance of an AC circuit. So XT is equal to XL minus XC. Because why it is XL minus XC? Because here omega L is nothing but your XL and 1 by omega C is nothing but your XC, capacitive reactance. Is it clear? So the Z is nothing but R plus J into X. R plus J into X. If you want to write the magnitude of it, which is nothing but root over R square plus XT square is your magnitude. So, right? So how we came across, this is a simple formula for a complex quantity. If you want to find the magnitude, root over A square plus B square. So R square plus XT square. So this is going to be about total circuit impedance. They ask about the derive the expression for the impedance of a RLC circuit. You can consider a series resonance circuit or any kind of parallel resonance circuit, and you can derive it. So it is nothing but the impedance is nothing but your resistance plus the reactance. Resistance plus reactance. So reactance we can have many terms over here. The reactance we are having many terms, that is the XL and XC, the inductive reactance and the capacitive reactance. The sum of the inductive and the capacitive reactance is going to be our total reactance. So why we came across this minus? Because we have converted into the complete complex quantity. So that is the reason why we came across here minus X. Right. Let us look into the response of it. So how we can plot the response for this? So this is going to give the inductive reactance, the response of the inductive reactance against the frequency. You can see here we are having the inductive reactance which is nothing but XL is equal to 2 pi FL, which is nothing but XL is equal to omega L. Omega L. So if you plot with respect to the frequency F, so which is nothing but XL is equal to 2 pi FL. So with respect to the frequency, so what could be the reactance here? From this equation easily you can say it is linearly increasing. The frequency is getting increased, obviously the inductive reactance is going to get increased. So what is the relationship here? It is nothing but the linear increase because it is a 2 pi, right? It is a 2 pi FL, multiplication of 2 pi FL, right? So XL is equal to, so this is going to be our inductive reactance against the frequency. So what could be the capacitive reactance? So what could be the capacitive reactance? So here, so let us plot the capacitive reactance. So here, the capacitive reactance, we know that the capacitive reactance Xc is nothing but, just now we have came across this equation, that is nothing but 1 by omega c. So omega is nothing but again here 2 pi f. So Xc is equal to 1 by 2 pi fc. So with respect to frequency here, inductive reactance is inversely proportional to the frequency of oscillation. So obviously here, there is going to be, when this inductive reactance, when the frequency is getting more, obviously the reactance Xc is going to getting decreased. You can see, right? So that means here, if you plot the inductive reactance and the capacitive reactance combinedly in a single plot, you can see the variation. Before that, again, let us consider a series RLC circuit. So where here, so either side of the resonance here, we can say the voltage drop is going to be equal to VL minus VC, because the reactance is, the net reactance is XL minus XC. Net reactance is nothing but XL minus XC. So we can say here it is nothing but VL minus VC. But at resonance, obviously, when the resistance is almost zero, that means at resonance, the voltage drop is going to be equal to 0, because it acts as a short circuit. It acts as a short circuit over there. So then we can have the reactance is going to be equal to 0, right? And the voltage drop is going to be equal to 0. Right. So now let us plot the total reactance XT with respect to the frequency. So we know that this portion, this line, linear line, we already seen this. This is nothing but, this indicates the response of the inductive reactance against the frequency. And the other one is going to indicate, this is going to indicate the capacitive reactance against frequency. So in the initial slide itself, in the definition, what we said is, when the admittances is getting cancelled each other, then at that particular frequency is nothing but your resonant frequency. You can see here, when this inductive reactance and the capacitive reactance, the responses are meeting at that point is nothing but here XL minus XC. So this is nothing but your resonant frequency. This is nothing but your resonant frequency. This point is nothing but your resonant frequency point. So at this side is going to be more capacitive, because this is going to be your capacitive line. So that means here the capacitance is more. It is more capacitive this side. From this below the resonant frequency, the circuit is going to be more capacitive, and above the resonant frequency, the circuit is going to be more inductive in nature. Why means, you can observe the same thing in the plot over here. So this plot, at this side, you can have the maximum value of the reactance, and whereas at this point, you can have the, after this resonant frequency, this point is going to have the maximum inductance, and this is going to have the maximum reactance of capacitive reactance. The value is going to be maximum, the reactance. So one important point I want to mention here, the units of the reactance is going to be same as the units of the resistance. It is nothing but ohms, right? So here, this frequency is nothing but the resonant frequency. So what is this point? At this point, this XL is going to be equal to XC. So that means at this condition, when this XL is equal to XC over here, so you can see, what is this XL? XL is nothing but omega L. Omega L is nothing but your 2 pi FL. What is XC? XC is nothing but 1 by omega C, which is nothing but 2 pi FC. 2 pi FC. Right. So now here, if we consider these two equations, cross multiplying these two, you can have f square is equal to f into f is going to be equal to f square is equal to 1 divided by 2 pi into 2 pi. 2 pi L is here and 2 pi C is here. So which is equal to 4 pi square, 4 pi square LC. So that means which is equal to f is going to be equal to root over 1 by 4 pi square LC. So from this we can simplify it as 1 by 2 pi root over LC. 1 by 2 pi root over LC. So now we can also write the angular resonance frequency is going to be equal to 1 by root C, and the angular frequency is going to be indicated using the radians, and the resonance frequency is going to be indicated using the H. So with respect to radians we can express, with respect to the frequency we can express. So when you are solving some problems, so they may ask you to, or they may give the value of the frequency in radians, or they may give the value of the frequency in hertz. So if they give the frequency in the hertz, you might use this formula. If they may give the frequency in radians, you might use this formula for calculating the inductance and the capacitance values. Right? So this is going to be our resonant frequency formula. For a series RLC circuit, this is going to be our resonant frequency. So what could be the impedance in a series resonative circuit? So if you want to calculate the impedance in a series resonative circuit, we have to include the resistance also. So at the resonant frequency, the resistance is going to be the minimum. So here we have to make a note that when the capacitive reactance dominates the circuit, the impedance curve is going to have a hyperbolic shape. But when the inductive reactance dominates the circuit, the curve is going to be the non-symmetrical because of its linear response of the inductive reactance. So in the previous slides we have seen it. That is, we have plotted the inductive reactance, which is the linear response, and we have plotted the capacitive reactance where we are having a hyperbolic shape. So here this portion is more capacitive and this portion is more inductive. So you can observe this when you are plotting the total impedance value, so this is going to be more perfect hyperbolic shape, whereas here this is not going to be perfect hyperbolic shape. Why? Because it is coming in non-symmetrical manner. Why? Because due to the linearity of its inductive reactance. Right. So what could be the circuit current at the resonance? We have plotted all the values. We have plotted the voltage, voltage, current, everything we are plotting. So what could be the circuit current with respect to the resonant frequency? You can see here at resonant frequency, obviously the resistance R is going to be at minimum value. In the previous slide that we have observed, the R is going to be minimum. The resistance is going to be minimum at the resonant frequency. So when the resistance is minimum, obviously the current is going to be the maximum. And then the left hand side, which is the more capacitive in nature, the I is going to be V by ZC, and the right hand side, the current I is going to be V by ZL. So ZL is nothing but the impedance of our circuit with respect to the inductance, and ZC is nothing but the impedance of our circuit with respect to the capacitance. And this is going to be I is equal to V by R. It is going to be the maximum value. So if you want to calculate the ideal value of the current at the resonant frequency, it is going to be infinity. The ideal value is going to be the infinity. But never, practically, never the resistance is not going to become equal to zero at any cost or at any case. The resistance never going to become equal to zero. But if you consider the ideal case, the resistance is going to be equal to zero, then the current, maximum current is going to be equal to infinity. The current is going to become infinity at the ideal case. So one important parameter which we have to define here is the Q factor. What do you mean by the Q factor? Q factor is nothing but the ratio of the voltage across the inductor or the capacitor to the applied voltage. So it is going to measure the voltage magnification in the circuit. It is going to measure the voltage magnification in the circuit at resonance. So what is the voltage? How much it is getting improved at the resonant frequency, whether it is getting improved or decreased or whatever is the case, that is going to define by a factor that is nothing but the quality factor or Q factor. Right? So which is nothing but the ratio of the voltage across the inductor or capacitor to the applied voltage. Right? So this quality factor Q is going to be equal to omega R L by R, or we can say which is nothing but the XL divided by R, which is equal to 1 by omega R CR. 1 by omega R CR, which is nothing but the inductive reactance over here, right? Inductive reactance 1 by omega RC, which is equal to XC by 1 by omega C is nothing but the XC divided by R, and omega into L is going to become XL. That is the reason why it is nothing but XL divided by R. So finally we can write it as which is equal to 1 by R root over L by C. 1 by R root over L by C. So if you cross multiply these two equations, XL by R is equal to XC by R. So obviously you are going to have this one 1 by R root over L by C. Right? 1 by R root over L by C. Because here you are having XC by R over here and XL by R over here. So you can have the total, the quality factor is going to be have the 1 by R root over L by C. 1 by R root over L by. So here this equation, how we came across this equation, if you want to know it. So let me give a small example, because here this omega R is nothing but the resonant frequency in radians, which is nothing but omega R is equal to 1 by root over LC. So let us consider this one. Q is equal to 1 by root over LC, because it is the omega R, 1 by root over LC into RC. Into R into C. So which is going to be equal to so 1 by R into root over LC we are having, and if you put the C in the under root, we are going to, this is going to become C square. So square and C is going to get cancelled, which is going to be equal to 1 by R root over L by C. 1 by R root over L by C. So this is how we came across the expression for the quality factor of a resonating circuit. So next let us go into the bandwidth of a circuit. Bandwidth of a circuit. So here for the bandwidth of the circuit, So the bandwidth here is nothing but, so the bandwidth within the limits of our lower and upper frequency, if you want to define. So the limits is nothing but your bandwidth. The limits between the lower and upper cutoff frequencies or the lower and upper threshold frequencies is going to be your bandwidth. Right? So here, let us plot the response of the current with respect to the frequency. So this is the response of the current with respect to the frequency which we have already plotted. So where this portion is nothing but your capacitive and this portion is nothing but your inductive nature. So where here you can observe the same thing over here. So with respect to the current, so when you are calculating the bandwidth, you are going to take the 3 dB point from the maximum current. So what is the 3 dB point? Minus 3 dB point lower cutoff frequency. So here is your 3 dB point, which is nothing but your 3 dB point is nothing but 0.707 times of maximum current. So what is the maximum current? Imax. So 0.707 into Imax is going to be your 3 dB point. So at this 3 dB point, you are marking 2 points with respect to the resonant frequency, right? With respect to the resonant frequency. So the left portion is going to be your lower cutoff frequency and the right portion is nothing but your higher cutoff frequency. So the bandwidth is going to become equal to FH minus FL. FH minus FL. So, but here you need to derive expression, the relation between the bandwidth and the Q factor. Bandwidth and the Q factor. So the expression is nothing but R by L radians or R by 2 pi L hedges. In terms of hedges means R by 2 pi L hedges. Right? So because here there is an important relation between the bandwidth and the Q factor, that is nothing but bandwidth is equal to FR by Q. Bandwidth is equal to FR by Q. So I can write bandwidth is equal to FR by Q, which is nothing but, what is the FR? FR is nothing but 1 by, you want in the radians, 1 by root over LC. 1 by root over LC is nothing but your resonant frequency. Right? So divided by Q factor. What is the Q factor value? Just now we have derived. What is the Q factor? Q factor is nothing but 1 by R into root over L by C. L by C. By calculating this one, you can say here, so R by root over LC into L by C. So here from this equation you can say this is going to get cancelled and C is going to get cancelled. So you are going to have R by root over L square, which is nothing but L. This is nothing but R by L radians. Why? Because R by L radians, because here we have taken a resonant frequency as 1 by root over LC. 1 by root over LC. That is the reason why we can't R by L. If we take here 1 by 2 pi root over LC, so obviously this R by L is going to multiply with the 1 by 2 pi. So then if you want to get in terms of H, this is going to be equal to 1 by R by 2 pi L. R by 2 pi L. This is going to be your expression in terms of H's. So this is going to be the bandwidth of your series resonating RLC circuit. So let us look into the properties of the RLC circuit, series RLC circuit. These are the key points which you have to remember. So in this, the applied voltage and the resulting current are in phase, which also means the power factor of the RLC resonant circuit is unity. The power factor is unity, right? So that's what we have. The first slide is going to describe this one. The power RLC circuit is unity. The power factor is unity. And the net reactance is going to be equal to 0 at resonance, because at resonance, the total reactance is going to become XL minus XC. You know that the total reactance is nothing but XL minus XC. At resonance, if XL is equal to XC, the net reactance is going to be equal to 0. And impedance is going to have only the resistive part. Impedance is going to have only the resistive part. And as here, the resistance is the minimum, the current in the circuit is going to be maximum. If you consider the ideal value, it is going to be equal to infinity. The current is going to have the maximum at the resonant frequency. Hence, this circuit is nothing but the acceptor circuit. Right? So at resonance, obviously the circuit is going to have the minimum impedance and the maximum impedance. So what is this impedance? Impedance is nothing but the reciprocal of impedance. If the impedance is minimum, obviously the impedance is going to be maximum. The frequency of the resonance is going to be given by Fr is equal to 1 by 2 pi root over LCR in terms of hertz, or in terms of radians, if you want to mention, it is nothing but 1 by root over LC. And the quality factor, you know that is nothing but 1 by R root over L by C is your quality factor, and the bandwidth is nothing but bandwidth is going to be equal to Fr by Q, which is equal to R by L or R by 2 pi L radians. So R by 2 pi L hertz or R by L radians. So these are the different properties of your series resonance circuit, right? Thank you for listening.